So here's the answer to how they control the speed for ions that are coming into a mass spectrometer. And I find this one interesting because it's a good application of concepts that we've learned already. So here's what they do. They make a chamber, and in this chamber they set up a magnetic field, a very stable magnetic field. And in this case, the magnetic field is coming up out of the page toward us. That's why we have the just the dots there. So we have a magnetic field rising up out of the page. And then they take their stream of ions, comes into the chamber here. These are the ions, and they have positive charges on them. And they go through, and they enter the chamber. Now we want them to pass straight through this if they're going the right speed. So in effect, we're trying to sort out the ions and only let through the ones that are going precisely the correct speed. So first, let's look at what this magnetic field will tend to do to these ions. They're positively charged ions, so we can use our right-hand rule. And let's see, the magnetic field is forefinger, that goes up. The velocity vector of the ions themselves is to the right, which means that the force on those ions is toward the bottom of the page as we look at it. That's the direction that the middle finger is pointing. That's the force on the ions is toward the bottom of the page here. So that means that the magnetic field will tend to bend the path of the ions downward. And the faster they're going, the greater the force and the more they'll get deflected downwards. So if they're, so that's the magnetic field. Now, at the same time, in addition to a magnetic field, they have an electrical field which is going parallel to the plane of the page, upward on the page. That's the direction of the electrical field. And again, these are positively charged ions, so if they encounter an electrical field which is going that way, that will tend to deflect the ions that direction. So we have a balance here between the electrical field and the magnetic field. The magnetic field is trying to deflect the ions toward the bottom of the page, and the electric field is trying to deflect the ions toward the top of the page. Now, the electrical force on all the ions is the same because the ions all have the same charge, but the magnetic field varies depending on how fast they are going, because the velocity of the particle, the velocity of the charge, is one of the factors in the force that's applying on it. The magnetic force is equal to QV sine theta beta. And so since velocity is one of the factors in the force that the magnetic field causes, the faster they're going, the more they'll get deflected down. So if they are going too slow, then the electric field has enough time to deflect them up, and they will miss the hole and they'll crash here or into the top of the chamber. And if they're going too fast, the magnetic field will exert too much force on them and they'll hit below. And only if they're going precisely the right speed will they go straight through the chamber and out the hole and into the mass spectrometer, which is over here. Okay, kind of a clever idea. Now, how can we figure out exactly how much, what the field needs to be? Well, you can tune it. We already have one of the equations here. This is the term for the magnetic field. Now, an electrical field, remember, electrical field is measured in newtons per coulomb, which is force per unit charge. We can rearrange that and we can get that the electrical force is equal to the electrical field times Q. By rearranging this, E equals F over Q, we get Fe equals EQ. And we want the electrical force to be equal to the magnetic force so that it's not the ions are not being deflected upward or downward. We want these two forces to be the same, which means we can set these equal to each other. So we get EQ equals QV sine theta beta. They set this up so that the ions are traveling exactly at a 90-degree angle to both the electrical field and the magnetic field, so the sine beta drops out. That comes equal to 1. We're talking about the charge on individual particles, individual ions, which is the same in both cases, so that cancels out. And we wind up then with the electrical field is equal to V times the magnetic field. And the speed that you want is this right here. So the speed is equal to the electrical field in newtons per coulomb divided by the magnetic field in Teslas. And how cool is that? This is newtons per coulomb. This is in Teslas. And you work out the numbers and you get a speed that you want. So for example, suppose we have a magnetic field equal to 50 Teslas and the electrical field is equal to 1,000 newtons per coulomb. We can set those equal to each other and we wind up with 1,000 times whatever the charge is that we're shooting through there is equal to the charge on the proton that we're shooting through there times V times the 50 Teslas. Now it turns out that the velocity then is equal to 1,000 divided by 50 or 20 meters per second. And you can work this backwards. If you know the velocity that you need to make your mass spectrometer work, and then you can just choose a convenient, well, I guess the magnets are usually the hardest thing to get. So you figure out what the field strength is for the magnets that you have, and then tune your electric field. Basically, you make this a giant capacitor in here, and create an electric field which balances it. So you find out what speed you want, what magnetic field you have, and figure out how strong an electric field you need. Anyway, kind of an interesting little application. Several years ago, AP2 had a free response question, which was kind of about this. I'll see if I can dig that out for you. That'd be a good one for you to look at when we're doing the review. So anyway, interesting application.